On November 9th, 2025, two astronomers in Germany pointed their large research telescope toward a faint, drifting smear of light in the constellation of Virgo. To anyone else, it would look like nothing more than a dusty blur, but they knew exactly what they were tracking. It was 3I Atlas, an interstellar comet that slipped behind the Sun roughly 2 weeks earlier. They began their routine. 5 long exposure images, 3 minutes each. The kind of simple, repeatable process astronomers perform hundreds of times a year. No drama, no expectations. Just data collection. But when they stacked the exposures and adjusted the contrast, the room fell completely silent. Jets emerged from the heart of the comet, thin, bright lines stretching outward like the spokes of a perfectly crafted wheel. Some pointed directly toward the Sunday, others extended into deep blackness. One of them reached more than 1 million kilometers into space, about 3 times the distance between Earth and the Moon. But length wasn't the shocking part, it was the shape. Every jet was perfectly straight, unnaturally straight. No curvature, no spiral, no blur from rotation. Just razor-sharp beams cutting through the void as if someone had taken a ruler and etched geometric lines directly onto space itself. That should be impossible, because 3I Atlas rotates once every 16 hours. And when any spinning object releases gas or dust, whether it's a lawn sprinkler throwing arcs of water, a firework spinning on the ground, or a typical comet venting material, those jets always twist. They curve outward in swirling corkscrews. That is how basic physics behaves. Every comet we've studied has followed those rules without exception, but not this one. These jets refuse to twist. They don't bend. They don't smear. They hold their orientation as if the comet's rotation simply doesn't matter, or as if something is actively resisting it. This is the 12th recorded anomaly, and it is the one that made 2 experienced astronomers step back from their screen, lower their coffee mugs, and whisper the question no one in their field wants to say out loud. What if this object is not behaving like a comet at all? Before we move deeper into the impossible geometry of these jets, take a moment to leave a like, and if you enjoy following these investigations, subscribe so you don't miss what comes next. Now, let's get back to the mystery. To understand why this single observation is so disturbing, we need to pull away from the telescope for a moment and look at something far simpler, something you can hold in your own hands. Imagine a tennis ball. Draw a small dot on it with a pen. Now spin the ball gently. As it turns, that dot traces a circular path through the air. And if that dot were releasing a thin trail of smoke, that trail wouldn't drift outward in a straight line. It would curve. It would spiral. It would wrap around the path set by the ball's rotation. You don't need equations for that. You can feel the logic in your fingertips. When the source rotates, and whatever it releases moves slower than that rotation, spiraling isn't just expected, it's guaranteed. Every real comet obeys this rule. When the Rosetta spacecraft visited Comet 67P, it saw jets erupting from its surface, and every one of them curved, just a little, a soft spiral, matching the comet's slow spin, exactly what physics predicts. But 3I Atlas refuses to play along. Its rotation period, 16.16 hours, is precise and confirmed. Teams around the world measured it by watching how its brightness shifted as different sides turned toward the Sunday. It's not an estimate, it's a measurement you can trust. And at the usual outflow speeds of cometary gas, around 400 meters per second, its jets should twist dramatically. Not a subtle curve, a huge, unmistakable spiral. Here's where everything falls apart. The longest jet from 3I Atlas stretches nearly 3 million kilometers. At 400 meters per second, the material in that jet takes around 87 days to reach its tip. And in those 87 days, the nucleus spins 129 times. If you were standing on that surface, releasing dust into space while spinning more than 100 times, the trail you create should coil into a massive corkscrew, one spiral for every rotation. But that isn't what the images show. Instead of a twisting ribbon, the jet is straight, perfectly, impossibly straight, ignoring rotation, ignoring geometry, ignoring physics. It should curve, it should bend, it should wrap itself through more than 100 spirals, but it doesn't. It stays straight. When the numbers refuse to cooperate with the story we expect, things become much clearer. 3i Atlas spins once every 16.16 hours. That works out to roughly 1.5 full rotations per day. Now, imagine one of its shorter jets, the ones that reach about 1 million kilometers into space. At the usual outflow speed of comet material, around 400 meters per second, that dust would take 29 days to travel the full length of that jet. And during those 29 days, the nucleus would complete 43 full rotations, 43 complete spins. Even that shortest jet should reveal 43 visible loops, curled around the comet like a stretched out spring or a loose corkscrew drifting through space. That's not a subtle effect. That's the kind of curvature you could spot even with imperfect data. Now consider the longest jet, the one stretching nearly 3 million kilometers. At 400 meters per second, the dust inside that jet takes about 87 days to reach its farthest end. And in that time, the comet rotates 129 times. These aren't small numbers. They aren't borderline cases. They aren't the kind of measurements where someone could say, maybe the curve is too faint to notice. We're talking about dozens upon dozens of rotations that should create enormous spirals. Spirals so obvious that any long exposure image would reveal them instantly. But every photograph shows the same thing: rigid, unwavering, perfectly straight beams. Frank Niebling and Michael Buchner, the German astrophotographers who captured the November 9th image, didn't rush to publish what they saw. They reached out quietly to colleagues, asking the one question they hoped someone else could answer: are we seeing this correctly? Is this geometry real? They wanted someone, anyone, to tell them they had made a mistake. Instead, observers across different countries, using different telescopes and different viewing angles, all reported the same result. The jets are straight. To understand just how impossible that is, picture something much closer to home. You're in your backyard on a warm afternoon, watering the garden. The hose sprays water in a smooth, predictable arc. Now start turning in a slow circle while holding the hose, and then a little faster, and then faster still. The water doesn't keep pointing in the same direction. It can't. It curves outward, spiraling around you as your rotation adds a sideways motion to the stream. The shape twists, loops, and wraps around your turning body, whether you want it to or not. Try to hold the stream perfectly steady while you spin. Try to keep it pointing in one exact direction. You can only do it by constantly adjusting your hand by deliberately turning the nozzle to counteract your own movement. A garden hose can only hold a fixed direction if you fight the rotation. Comets don't have hands. They don't have nozzles. They don't have guidance systems or thrusters or mechanisms that compensate for motion. They simply release gas and dust, and the laws of rotation shape whatever comes out. Unless they're not behaving like comets at all. One of the first explanations scientists reached for was the simplest one: fragmentation. Maybe the nucleus of 3i Atlas had cracked apart. If the comet split into several pieces, each drifting a little differently, each shedding its own material, then those separate dust streams might appear from far away, like jets that don't spiral. They wouldn't come from a rotating source at all. They'd just be multiple debris trails lying next to each other, each one straight because each fragment moved in a fixed line. This idea wasn't far-fetched. Comets fragment all the time. The heat from the sun creates intense thermal stress. Frozen pockets of gas expand and explode outward. Rotation, even gentle rotation, can tear a body apart if the internal structure is weak. Many of the famous comets we've studied have cracked into pieces under these forces. It is a normal, documented, expected behavior. So fragmentation seemed like the most reasonable answer. But that possibility collapsed almost immediately. On November 11th, astronomers David Dewitt and Jane Liu, two of the most experienced comet observers alive, and the same pair who helped uncover the Kuiper belt, pointed the Nordic Optical Telescope at 3i Atlas specifically to test this idea. They weren't looking for jets. They weren't looking for brightness variations. They were searching for fragments, tiny secondary points of light, faint companions, miniature shards, anything that would indicate the nucleus had broken apart. What they found was the opposite. The images showed a single, clean, intact nucleus, one bright central condensation, surrounded by a soft, diffuse coma, no trailing pieces, no ghostly secondary dots, no evidence of cracking or shedding, nothing that suggested violent breakup. It was exactly what you'd expect from a stable, cohesive comet, which means the straight lines aren't debris trails. They are real. Jets material actively leaving the surface while the nucleus rotates beneath them. And that brings us to the next attempted explanation, the velocity problem. Some scientists asked whether the outflow speeds might be drastically higher than normal. Perhaps the gas wasn't moving at the usual 400 meters per second. Maybe it was blasting out at several thousand meters per second fast enough that the jets would reach their full length in just a few days instead of months. If the material traveled 3 million kilometers in a handful of days, the comet would only rotate a few times during that period. Spiraling patterns might then become so shallow that they'd be nearly invisible, even in long exposure photographs. At first glance, that sounds reasonable. Fast-moving material leaves less time for rotation to twist it. But the physics falls apart when you try to calculate whether such speeds are even possible. Gas velocity depends on temperature. It's not random. It's not arbitrary. Molecules move faster when they're hotter and slower when they're colder. For carbon dioxide, the primary gas escaping from 3I Atlas, the speed of the gas is set by the temperature of the comet's surface, which is set by how much sunlight it receives. At 1.36 astronomical units from the Sun, its closest approach, the comet's surface probably warmed to somewhere between 200 and 250 Kelvin. That's cold by Earth standards, but typical for a comet. And at those temperatures, carbon dioxide gas reaches speeds of roughly 400 to 500 meters per second. It cannot naturally reach thousands. To accelerate carbon dioxide to several thousand meters per second, the surface would need to be heated to at least 20,000 Kelvin. That's hotter than the surface of the Sun itself. There is no known natural process, no chemistry, no physics, no internal reaction that can heat a comet's interior surface to 20,000 Kelvin, especially one this small and this far from the Sunday. So the high-velocity theory tries to fix one impossibility by creating an even larger one. The jets remain straight. And none of the explanations rooted in ordinary comet physics fit the observation. Another explanation scientists reached for was deceptively simple. Maybe we were seeing the jets from just the right angle to hide their spiraling motion. Astronomy is full of tricks of perspective. A spiral galaxy can look like a straight line when viewed edge-on. A spinning asteroid can appear almost motionless if its rotation axis points toward you. Even a twisting shape can appear flat when your viewpoint compresses its curves. So the idea took shape. Could the spirals be there, but hidden by our angle of view? Imagine standing at the top of a spiral staircase. If you look straight down, the staircase doesn't look like a twisting structure. You don't see the shape turning. You see a pattern of circles layered on top of one another. The true geometry is still there, your viewpoint just conceals it. Perhaps the jets of 3I Atlas worked the same way. Maybe we were looking almost directly along the axis of rotation for one of the jets. From that vantage point, even a dramatic spiral could appear nearly straight. And at first glance, this explanation almost worked. For a single jet, yes, the angle could flatten the curve, but the November 9th images show several jets, not one. They radiate outward in different directions like the spokes of a wheel. One stretches nearly toward Earth, another points away. Others angle sideways, diagonally, or nearly perpendicular to our line of sight. They cannot all be oriented in the one exact way required to hide their spirals. Statistically, at least one of them should reveal curvature, a loop, a bend, some hint of rotation twisting the material through space, but none of them do. Every jet, no matter its direction, remains perfectly straight, the kind of straight that does not care about our viewpoint, the kind of straight that should not exist if the object beneath is rotating once every 16.16 hours. This was the moment when astronomers began realizing just how deep the problem ran. One by one, the natural explanations were falling apart. First, the rotation. The comet absolutely spins. That number, 16.16 hours, comes from independent, consistent measurements taken by multiple teams using brightness variations, a method reliable enough to determine rotation periods for hundreds of comets and asteroids. Second, the length of the jets. These beams stretch for millions of kilometers. Their size isn't inferred or guessed. It's calculated through basic angular measurements, simple trigonometry that doesn't leave much room for error. Third, the velocities. Gas driven by carbon dioxide sublimation only reaches a few hundred meters per second at the temperatures 3I Atlas experiences. Molecules cannot reach thousands of meters per second without being heated to at least 20,000 Kelvin hotter than the surface of the Sunday. There is nothing, no natural chemical, geological, or thermal process that can generate such temperatures inside a comet. Fourth, the geometry. A rotating object venting gas must produce spirals. It is not a special case. It is not an exception. It is basic, unbreakable rotational kinematics. And yet, the spirals are missing. So the situation reduces to a handful of possibilities. Perhaps the rotation measurements are wrong, but they are not. The data is far too consistent across too many teams. Perhaps the jet distances are wrong, but they are not. The math is straightforward, and the observations repeat across telescopes. Perhaps the velocities are wrong, but they are not. Thermal physics locks those speeds in place, and spectroscopy in December will confirm it. Perhaps the geometry is wrong, but it cannot be. This is fundamental motion that governs everything from spinning fireworks to planetary atmospheres. With all natural explanations collapsing, scientists are forced toward a single, unsettling conclusion. Something else is happening here, something outside the behavior of ordinary comets, something that does not fit comfortably inside the boundaries of known physics, something that makes experts hesitate before speaking the next logical thought aloud. And that quiet hesitation may be the most revealing data point of all. If the jets are not spiraling, then something must be preventing them from spiraling, because spiraling is not optional. It is not a feature that can appear or disappear. It is the unavoidable consequence of rotation. If the nucleus of 3I Atlas is turning once every 16.16 hours, then anything leaving its surface must twist around that rotation. So the only way to stop the twisting is to cancel the rotation. For a natural comet, that should be impossible. There is no known mechanism embedded inside these icy, dusty bodies that can resist rotation. When a comet spins, the entire structure spins. The crust spins. The vents spin. The gas vents spin. Everything is locked together. You cannot have a comet rotating beneath your feet while the jets it releases stay perfectly aligned with the same direction in space. It would be like standing on a spinning carousel and watching the horses remain motionless relative to the horizon. The platform turns underneath you, but the horses do not move. That cannot happen unless some invisible system is actively fighting the rotation. And that brings us to the strange, uncomfortable possibility scientists rarely talk about openly. The only objects we know of that can rotate while keeping certain components perfectly stable are engineered objects. Modern satellites do this every day. Many of them spin for structural stability or thermal balance, but their antennas, cameras, and solar arrays remain locked onto their targets in fixed orientations. They achieve this through reaction wheels, heavy spinning disks inside the spacecraft, or through control moment gyroscopes that shift angular momentum around the structure. These systems let a spacecraft rotate, while individual instruments behave as if the rotation is not happening at all. A rotating body with components that stay fixed in space. Exactly what we are observing from 3I Atlas. Of course, comets are not spacecraft. They don't have reaction wheels buried beneath their crust. They don't carry momentum control gyros humming in their cores. They don't realign themselves to counteract motion. But then the question hangs in the air, quiet, subtle, and unsettling. If these jets remain perfectly oriented despite the nucleus spinning beneath them, then what, exactly, is holding them steady? What force, what mechanism, what internal structure could possibly compensate for rotation inside a natural object made of dust, ice, and loosely bonded rock? If this were a typical comet, the answer would be simple: nothing. Absolutely nothing. And yet, that is not the answer here. So scientists are left staring at an implication they do not want to voice. The kind of implication that would normally be dismissed immediately. The kind that belongs in speculative fiction not in a peer-reviewed discussion of interstellar bodies. But the data doesn't care about comfort. The jets behave exactly like the stabilized emissions of a rotating spacecraft, and if that similarity is real, even faintly, even partially, then we are forced to reconsider what 3i Atlas truly is. Because comets do not stabilize their emissions. Spacecraft do. To truly understand why these straight jets are so unsettling, we need to slow down and look at something fundamental, something so basic that it applies to basketballs, spinning toys, planets, and every comet ever observed. It is the physics of rotation. Imagine holding a basketball in your hands. You give it a spin on your fingertip. As it turns, every point on that ball, every tiny piece of paint, every seam, every speck of dust moves along a circular path. Points near the pole trace tight little circles. Points along the equator sweep out wide arcs. But everything rotates together. Nothing stays still while the rest spins around it. Now imagine painting a stripe around the middle of that basketball. Spin the ball again. If you watch carefully, the stripe blurs into a continuous band, a ring of colour smeared by motion. And if you drilled a hole into the side of the ball and released air or smoke while it rotated, that escaping material wouldn't stream out in a straight line. It would spiral outward, wrapping around the direction of rotation exactly the way logic insists it must. This isn't theory. This isn't advanced physics. This is rotational kinematics geometry as solid and certain as saying 2 + 2 = 4. And this same principle applies to 3i Atlas. Its rotation period, 16.16 hours, means that if the nucleus is roughly 5 kilometers across, the equator is moving at around 1,000 meters per second. That is fast. Not Earth-level fast, our equator moves at about 460 meters per second, but fast enough that anything released from the surface should show the unmistakable signature of rotation. And in one sense, the comet behaves exactly as expected. We see material spraying outward. We see those jets stretching millions of kilometers into space. The comet is clearly venting gas and dust the same way every active comet does. But what we do not see is the key. The material does not spiral. For it to remain straight, one of two things must be true. Either the gas is travelling so incredibly fast that the comet's rotation becomes irrelevant, which is impossible at the temperatures this comet experiences, or something is compensating for the rotation, some mechanism, some control, some structure synchronized with the spin in a way we have never seen in natural objects. To feel how strange this is, think of a lighthouse. A lighthouse sends out a bright beam of light that slowly rotates, sweeping across the ocean once every 30 seconds. If you took a long exposure photograph of that lighthouse, you would capture a perfect circle of light, one complete rotation of the beam. Now change the thought experiment slightly. Imagine the lighthouse is not shining photons, but releasing slow-moving fireflies. Each firefly drifts gently through the air for 2 minutes before fading away. If you took a long exposure photograph of that scene, you wouldn't get a circle, you'd get a spiral. Fireflies released early in the spin would drift outward in one direction, while new ones emerge as the lighthouse turns. The traces of these paths overlap and twist, revealing the rotation in their shapes. This is exactly what should happen with a comet. As the nucleus rotates, sunlight heats different regions at different times. Active vents release gas and dust continuously. Material released an hour ago is still visible. Material released 3 days ago is still drifting outward. And during all that time, the nucleus keeps turning. Every minute of rotation should leave a mark on the jet. Every turn should twist the path. The spiral should be unavoidable. Unless the source of the jet can adjust itself, unless it can counteract the rotation so perfectly that the jet remains locked to the same place in space. Like a lighthouse keeper grabbing the lamp and turning it by hand to keep it aimed at one exact point outside, even as the tower beneath them rotates. Humans can do that. Machines can do that. Anything with control, intention, or guidance can do that. But a chunk of ice and rock drifting through space cannot. 3i Atlas should not be able to behave this way. And yet it does. There is one more way to understand the impossibility of what we're seeing, and it involves something as simple as a kettle on a stove. Imagine placing a metal kettle over a flame. As the water heats, steam begins to rise from the spout in a clean vertical column. As long as the kettle remains still, that column stays perfectly straight. Now reach out and spin the kettle gently while the steam escapes. The moment the body begins to turn, the column of steam bends. It curves away from the original line, twisting into a soft corkscrew shape because the spout is moving beneath the rising plume. You cannot spin a kettle and expect the steam column to remain straight. It will always bend, always curve, always show the signature of rotation. This isn't a special case. This is the way motion works in a rotating system. The only way to keep that steam column pointing in the same direction while the kettle rotates is to physically detach the spout from the rotating. The body almost like mounting the spout on a bearing or a pivot, allowing the kettle to spin while the spout stays fixed in place. That would require moving parts. It would require deliberate design. It would require the kind of internal mechanism you find in machines, not in household cookware, and certainly not in natural comets. Yet 3i Atlas behaves as if its jets are not connected to the spinning nucleus beneath them, as if the source of each jet is somehow insulated from rotation, able to maintain its orientation even as the body turns. That is the kettle test spelled out in the vacuum of space, and Atlas is failing it spectacularly. Or, depending on how you look at it, it is succeeding in a way no natural comet can, but the most unforgiving part of this mystery comes from the mathematics. So let's lay out the numbers one more time, slowly and clearly, in a way that anyone can follow. The comet rotates once every 16.16 hours. That number comes from multiple observing teams using different telescopes in different parts of the world. It is not a rough estimate. It is a confirmed rotational period. The longest jet extends roughly 3 million kilometers into space. That distance comes from simple angular measurements, just geometry applied to a known object at a known distance. Again, not speculation. The gas leaving the surface is primarily carbon dioxide. At the distance of 1.36 astronomical units from the Sun, the surface temperatures allow this gas to reach speeds of about 400 meters per second, not thousands, not even close. Now take the full length of the jet, 3 million kilometers, or 3 billion meters, and divide it by the outflow velocity of 400 meters per second. The result is 7,500,000 seconds of travel. Convert that into days and you get roughly 87 days. During those 87 days, the comet completes 129 full rotations. So the expected shape of the jet is not a spiral with one loop. It is not 10 loops. It is not 50 loops. The expected shape is a corkscrew with 129 full turns, an enormous twisting ribbon stretched across 3 million kilometers of space. And yet every telescope pointed at 3i Atlas shows the same thing, a straight line, not a gentle spiral, not a curve barely too small to detect, a straight, rigid, unwavering beam. That leaves us with only a few possibilities, and none of them are comfortable. One possibility is that the travel time is wrong, but to reduce the travel time enough to eliminate the spiral, the gas would need to move at 5,000 meters per second or more. That would require temperatures hotter than the surface of the Sunday. Nothing inside a comet can reach those temperatures. Another possibility is that the rotation somehow doesn't affect the jets. That would require a mechanism capable of compensating for rotation, something like a gimbal or a stabilization system. Nothing like that exists in natural cometary physics. And the final possibility is the one no one wants to say aloud, that 3i Atlas is not following the rules that govern natural comets. Something about this object refuses to behave like the icy wanderers we have studied for centuries. Something is resisting rotation in a way that should not be possible for rock and ice alone. Whatever the cause, the mathematics cannot be argued with, the geometry cannot be rewritten, the physics cannot be negotiated, and yet the jets remain straight. There is another concept we need to explore, one that comes from engineering, not astronomy. Because if something is holding those jets steady while the nucleus rotates beneath them, then whatever is happening inside this object resembles a principle we use in spacecraft every single day. To understand it, picture a satellite in orbit. It might be spinning slowly for stability, its metal shell turning smoothly through the vacuum. Yet at the same time, one of its instruments, a camera, a dish, a telescope, remains locked onto a star or a planet with perfect precision, the outside rotates. The inside stays steady. How? The trick is a device called a reaction wheel. Inside the spacecraft is a heavy disk mounted on an axis. When the disk spins faster, the spacecraft turns slightly in the opposite direction. When the disk slows down, the spacecraft rotates back. It is the simple law of angular momentum used with surgical precision. Add 3 reaction wheels, one for pitch, one for roll, one for yaw, and you can control orientation in all directions. Engineers can make the spacecraft body spin while keeping a narrow antenna pointed at Earth. They can rotate a telescope while holding its mirror fixed on a distant galaxy. These systems have been flying since the 1950s. Every modern observatory uses them. Every deep space probe depends on them. Now, imagine something startling. If 3i Atlas had something inside it that acted like a reaction wheel, if some internal mechanism allowed it to hold a jet steady while the nucleus rotated, then the straight, unwavering beams we see would make perfect sense. They would be exactly what you would expect from a rotating object with stabilized outputs. But that possibility demands things comets do not possess. It would require an internal structure far more complex than porous ice and dust. It would require mechanisms capable of surviving billions of years in deep space. It would require design. It would require engineering. It would require intention. And nothing about natural comet formation includes those ingredients. This leaves one final natural hypothesis, one last lifeline that planetary scientists consider before stepping into far stranger territory. What if the jets are not made of ordinary gas at all? There is a possibility, slim but real, that what we are seeing is plasma ionized particles accelerated by powerful electromagnetic forces. Most comets do not produce their own electric fields, but space is not gentle. Cosmic rays strike surfaces for billions of years. Charge builds up. Materials separate. Under rare conditions, a solid body may develop strong electrical fields or interact intensely with the solar wind. Plasma behaves very differently from slow-moving sublimated gas. Plasma can accelerate to thousands, even tens of thousands of kilometers per second. At those extreme speeds, a jet could cover 3 million kilometers in only a few hours. In that shortened travel time, the nucleus would complete only a handful of rotations. The spiraling that should be obvious becomes tiny, compressed, barely noticeable. Straight jets suddenly become possible. This idea is unusual, but it does not violate physics. It is exotic, but not supernatural. And most importantly, it is testable. Plasma glows in very specific ways. It produces bright, emission lines at wavelengths that betray the ionization state of the atoms. It generates unusual line ratios. It creates Doppler shifts that reveal incredible speeds. In December, when spectroscopy is performed, the fingerprints of plasma will be unmistakable if plasma is truly what we are seeing. If the jets contain ionized carbon, ionized oxygen, or any of the hallmarks of electromagnetic acceleration, then we may have discovered a rare kind of comet. Strange, powerful, but natural. But if the spectra reveal ordinary cometary molecules, carbon dioxide, water vapor, carbon monoxide moving at ordinary speeds, and the jets remain perfectly straight in the weeks that follow, then every natural explanation collapses, and we will be left with something far more unsettling. We are now standing at the edge of something, unsettling the point where every natural explanation begins to bend under its own weight. Every idea scientists have proposed so far is technically possible, but only if we are willing to stack improbability on top of improbability. Take the high-velocity outgassing hypothesis. For the jets to stay straight, the gas would need to leave the surface at speeds of several thousand meters per second, but achieving that requires temperatures hotter than the sun's surface 20,000 Kelvin or more. There is no known natural way for a small body drifting through interstellar space to reach those temperatures without vaporizing entirely. Then there is the plasma explanation. It would require 3i Atlas to possess electromagnetic properties unlike any comet ever observed. Not just unusual, unprecedented. Powerful enough to strip electrons, accelerate particles, and launch ionized beams millions of kilometers long. It is exotic, yes, but at least it exists within the realm of physics. And better yet, it can be tested. but it still demands behavior we have never actually seen in a natural nucleus. The viewing angle idea sounds simple at first, but it collapses quickly. You can hide the curvature of one jet if it happens to align perfectly with our line of sight, but the November 9th image shows several jets pointing in different directions. Some tilt toward us, some away, some broadside. For the spiraling to be invisible in all of them, every single jet would have to be oriented just right. The geometry required for that is not just unlikely, it borders on impossible. And then there is synchronized pulsing. Some comets outgas in bursts, releasing material in short, rhythmic jets. But even then, the bursts follow the rotation. The pulse emerges when the active region faces the sun, and it vanishes when the region rotates into darkness. For the jets to appear straight, those pulses would have to fire at precisely the right moment, again and again, in perfect alignment, compensating for rotation with flawless timing. There is no known sublimation mechanism that can do that. Each of these ideas attempts to rescue a natural explanation, and each, in doing so, must introduce new problems, new assumptions, new miracles of coincidence. When you pile enough unlikely assumptions together, eventually you have to pause and ask a very uncomfortable question. Is the natural explanation actually more plausible than the alternative? Because the alternative is not random. The alternative fits the data cleanly. The alternative explains the stabilization, the directional control, the fixed jet orientation, the resistance to rotation. The alternative is that something inside this object is maintaining those beams deliberately using mechanisms, principles, or technologies that resemble active stabilization. That possibility sounds extraordinary, but so does a comet that ignores the geometry of rotation. So does a comet that releases jets which refuse to curve over more than 100 full spins. So does a comet that behaves in ways completely unknown to cometary science. Sometimes the extraordinary explanation is not the wild one. Sometimes it is simply the one that fits the evidence without needing a tower of coincidences to hold it up. And 3i Atlas is inching us toward that realization. The deeper astronomers look into 3i Atlas, the harder it becomes to pretend the anomalies are isolated. The straight jets were alarming enough, but they're not the only thing that's wrong. They're simply the 12th entry on a list that has been quietly growing for months. And here's the part no one likes saying out loud. Each anomaly on its own can be explained away if you try hard enough. You can blame an instrument, or the viewing angle, or a quirk of thermal physics. You can shrug and say, maybe. But when you stack all the anomalies together, they stop behaving like coincidences. They start forming a pattern that makes people very uncomfortable. So let's start at the beginning, long before the jets, before the November observations, before anyone noticed anything unusual at all. The very first red flag appeared the moment 3i Atlas arrived in our solar system. When astronomers calculated its incoming trajectory, they found that it entered our planetary neighbourhood with its path tilted just 5 degrees above the ecliptic plane, the flat disk where the planets, moons, and most asteroids orbit. To appreciate why that matters, picture the solar system floating inside a giant sphere. The ecliptic plane, the thin band where the planets orbit, is like a narrow ribbon wrapping around the sphere's middle. Interstellar objects are expected to approach from anywhere on that sphere, above, below, sideways, diagonally. There is no preferred direction in deep space. It's completely random. Hitting that narrow ribbon by chance is extremely unlikely. Roughly 0.2%, 2 chances out of 1,000. Not impossible, but uncomfortably precise. And here's the part that bothers dynamicists the most. Entering near. The ecliptic isn't just convenient, it's strategically advantageous. From that angle, the object can pass by every major planet without burning energy. It naturally follows the same orbital lanes human spacecraft use when performing multi-planet flybys. It's the position you choose if your goal is to study a planetary system efficiently. For a natural comet, this alignment is a statistical outlier. For something engineered, it's exactly the kind of arrival you'd design. And this was only the first anomaly noticed quietly, logged without fanfare, and then largely ignored, because no one expected what would come next. The next warning sign appeared months before the straightjets were ever photographed. Beginning in July, astronomers kept noticing something they didn't talk about much at first because it wasn't supposed to happen at all. 3i Atlas had a jet pointing toward the Sunday. Normally, a comet's tail always streams away from the sun, pushed back by sunlight and the flow of charged particles called the solar wind. It's one of the most reliable behaviors in astronomy. Sun on one side, tail on the other. But in this case, observers around the world were seeing the opposite, a bright, persistent structure extending in the sunward direction. This wasn't a faint artifact or a trick of poor imaging. It was clear, it was stable, and it lasted from midsummer all the way into November. That alone makes it profoundly strange. Anti-tails can appear in rare cases, but only because of perspective. When Earth passes through a comet's orbital plane, dust trails can briefly look like they're pointing at the sun, even though they're not. These events last a few days, maybe a week. You blink and they're gone. But 3i Atlas kept its sunward feature for months. That means the material was genuinely moving toward the sun, pushed inward against the force of radiation pressure that should have driven it outward. There is a natural explanation, but it's a stretch. To resist sunlight for that long, the particles must be enormous, thick, heavy dust grains, or even pebble-sized chunks, big enough that light simply couldn't push them. Possible? Yes. Common? Absolutely not. But there's another explanation that makes astronomers shift uncomfortably in their chairs. If the object was slowing down, actively reducing speed as it approached the sun, a sunward jet wouldn't be strange at all. It would be a controlled burn, a braking maneuver, something a probe would do to match the orbital plane, adjust trajectory, or prepare for a close observation pass. Again, nothing proven. But the coincidence sits heavily with the other anomalies. And then there's the matter of its size. When astronomers estimated the diameter of 3i Atlas from its brightness, they ended up with a number between 3 and 6 kilometers. That makes it dramatically larger than any interstellar object we've seen before. Our first visitor, Oumuamua, was only a few hundred meters long, small enough to fit inside a football stadium. The second, 2i Borisov, was around 1 kilometer across, but this one, possibly 5 kilometers. Natural populations of space debris follow what's called a power law distribution. In simple terms, small objects are everywhere and big ones are extremely rare. You should stumble across countless tiny wanderers before ever encountering a massive one, but the third interstellar object we've detected is one of the largest possible. That's not what statistics predict. Either we're unbelievably lucky, or interstellar space is full of large bodies in a way no model has ever suggested, or this object wasn't ejected randomly from a planetary system like the others. Maybe its size isn't an accident. Maybe it was built to be that size. One anomaly might be a coincidence, two might be noise, but by this point in the timeline, scientists had already logged 3, and the pattern was just getting started. Another detail slipped into the growing list of oddities, one that seems harmless at first glance, but becomes unsettling once you run the numbers. As 3i Atlas made its way through the inner solar system, its path didn't just drift randomly past empty space. It passed extraordinarily close to 3 major planets. On October 3rd, it swept within about 29 million kilometers of Mars. A few weeks later, in late October, it came within 97 million kilometers of Venus. And next year, in March 2026, it will pass only about 54 million kilometers from Jupiter. Now, close planetary approaches do happen. Space is enormous, but gravitational paths are messy, and coincidences occur. The problem is the probability of this particular sequence. When you run the statistics, the chance that a random interstellar object would come this close to 3 different planets on a single inbound pass is around 0.005%, about 1 in 20,000. That doesn't mean it's impossible, but it does raise eyebrows. Because if you were designing a reconnaissance mission to study a planetary system, you wouldn't wander aimlessly. You'd plan a trajectory that gives you sweeping gravity assists and ideal observation distances. You would deliberately aim for planetary flybys. And 3i Atlas's path looks a lot more like a tour than an accident. And then, just as astronomers prepared for its most energetic phase, the moment when the object would get closest to the sun, all available ground-based observations suddenly went dark. Perihelion happened on October 29th, 2025, but from Earth's viewpoint, that moment occurred directly behind the Sunday. The object passed through its brightest, most active, most revealing stage, completely hidden from every optical telescope on the planet. The only instruments capable of observing it were a handful of spacecraft, coronagraphs designed to block sunlight. Was that a coincidence? It could be. Perihelion can occur anywhere along an orbit. The Sun doesn't set a schedule. This alignment isn't impossible, it's just inconvenient. But it does mean that whatever happened during the object's most active and volatile period, outgassing, fragmentation, acceleration, stabilization, none of it was seen from Earth. The timing created a perfect observational blind spot for the one civilization capable of studying it in detail. If the object was simply a natural comet, that would just be frustrating. But if someone or something wanted to perform high-activity operations away from Earth's instruments, the timing couldn't have been better, and the list keeps growing. Another strange behavior showed up when spacecraft coronagraphs finally caught a glimpse of 3I Atlas during perihelion the moment it passed closest to the Sunday. As the object slipped behind the Sun from Earth's point of view, something unexpected happened. Its brightness surged far beyond what any model predicted. Instead of following the normal curve that comets obey, it grew roughly 2 magnitudes brighter than expected. In simpler terms, it became about 6 times more luminous than it should have been. Now, comets can brighten suddenly. When pockets of frozen gas deep inside the nucleus crack open, they can erupt outward in a violent burst. But these events are short, hours, maybe a day or two at most. They spike, flare, then fade. 3I Atlas didn't spike, it didn't flash, it stayed bright. The elevated brightness persisted throughout its entire perihelion passage. That's not an outburst, that's sustained energy output. If the brightness came from massive outgassing, we should see debris, clouds of dust, expanding shells, obvious asymmetry. But the coma structure didn't show the signs you would expect from a dramatic internal rupture, which leaves the uncomfortable alternative. Maybe the brightness wasn't just reflected sunlight, maybe it came from something else. And the oddities didn't stop there. During perihelion, instruments detected a noticeable shift in colour, a distinct blue tint. Not slightly blue, not a mild bias. It was bluer than the Sun itself. That should not happen. When sunlight bounces off comet dust, the scattering process naturally reddens the light. It removes shorter wavelengths and leaves the longer, redder colours behind. That is basic physics, something every comet ever studied has obeyed. For 3I Atlas to appear bluer than the star illuminating it means something unusual was happening near its surface. There are a few possible explanations. One is extremely fine dust, smaller than what we typically see, capable of scattering light in an unusual way. Another is strong emission from ionized gases, especially ionized carbon monoxide, which can glow in blue wavelengths under the right conditions. That second explanation, technically natural, but the level of ionization required is unusually high. You would need intense energy input, sustained over time, and not just a brief flare. And then there is the third possibility, light that isn't produced by sunlight at all. Light generated through some non-thermal process, something we don't normally see in comets. Something that would imply energy sources or mechanisms beyond standard sublimation. Most scientists lean toward the ionized gas explanation because it is the least radical, but even that requires conditions we haven't observed in typical comets. And when you layer this blue glow on top of the sustained brightness surge, on top of the hidden perihelion, on top of the improbable trajectory, the story becomes harder to dismiss as coincidence. Another strange clue appeared months earlier, long before the straitjets shocked anyone. In August, astronomers using the Very Large Telescope detected vaporized nickel surrounding 3I Atlas. That would be normal if the comet was scorching hot nickel boils at nearly 3,000 degrees Celsius. But the gas was detected at around minus 150 degrees. At those temperatures, nickel should be solid metal, frozen and completely inert. Yet there it was, drifting around the nucleus as vapor. Researchers proposed explanations, cosmic ray chemistry, tiny meteor impacts, exotic chemical reactions, but none of them are confirmed. All are speculative. and none fully explain how metal can exist as vapor at temperatures far below its boiling point. Then came another puzzle, the missing mass. After perihelion, tracking data suggested that the comet experienced subtle non-gravitational acceleration. The simplest interpretation is mass loss. If you run the numbers, it implies that somewhere between 10 and 13% of the comet's total mass disappeared. That equals roughly 3 to 5 billion tons of material. Losing that much mass should produce a gigantic debris cloud, millions of kilometers across. Any telescope on Earth would see it immediately, an enormous fan of dust expanding behind the comet like smoke from an explosion. But in November, when astronomers looked again, the coma was modest, the nucleus was intact, and no vast debris field existed anywhere around it. So either the mass loss calculations are wrong, or the debris somehow became invisible, or the acceleration we measured wasn't caused by outgassing at all. December's spectroscopic data will settle this. If the comet is blasting out huge amounts of gas, then the natural explanation survives. If gas output is modest, then the acceleration must come from another source entirely. And then there is the chemical mystery. Observations from the James Webb Space Telescope revealed a carbon dioxide to water ratio of 8:1, one of the highest ever recorded in a comet. Most comets are dominated by water ice. To find one that is mostly carbon dioxide implies it formed in an extremely cold region, far from its parent star, where carbon dioxide froze out more readily than water. Unusual, yes, but at least explicable. It tells us something about the comet's birthplace, cold, distant, and deeply frozen. But the structural mystery is harder to dismiss. Given the intense heating at perihelion, the rapid rotation, and the expected pressure from vigorous outgassing, many scientists predicted that 3I Atlas would fragment. Comets break apart under far less stress all the time. But when images from November 11th arrived, they showed one solid nucleus, no cracks, no companion fragments, no evidence of disintegration. Either this object has a far stronger internal structure than typical comets, or our stress models are wrong, or the supposed mass loss never happened. And all of this circles back to the 12th and most troubling behavior, the locked jets. The jets that remain perfectly straight despite more than 120 rotations during their formation. The jets that maintain stable orientation relative to the Sun while the nucleus spins beneath them. This anomaly isn't just unusual. It isn't just rare. It violates the basic physics that govern natural comets. It behaves as if something is actively controlling the direction of those jets, or preventing them from spiraling, or maintaining stability through a mechanism no comet should possess. When one anomaly crosses into the realm of the impossible, it forces us to re-evaluate the rest. Maybe these behaviors aren't isolated oddities. Maybe they're pieces of the same picture. Maybe they're not coincidences at all. There's one more layer to all of this, and it's the one that keeps experienced scientists awake at night. Not because of any single anomaly, not because of 3 of them, not even because of half a dozen. It's because there are 12, and when you deal with 12 unlikely events in the same object, the wait stops. Feeling random. Think of it like flipping a coin. 1 head is normal, 2 in a row is still ordinary, but 3 heads in a row? That's a 1 in 8 chance. 4 in a row becomes 1 in 16. 5 drops to roughly 1 in 32. And by the time you reach 12 heads in a row, the probability shrinks to about 0.024%, roughly 1 in 4,000. At that point, you stop assuming the coin is fair. You start asking whether something else is influencing the outcome. That's the position scientists are in now. Each anomaly surrounding 3I Atlas can, in theory, be explained away by some rare circumstance. But taken together, the odds of all 12 lining up naturally become so small that the idea demands examination. It doesn't prove an artificial origin. It doesn't prove deliberate engineering or technological intent. But it does make those possibilities worth considering with an open, rational mind. When coincidences stack this high, they stop behaving like coincidences. And that's why December matters so much. The most important observations arrive in just a few weeks. On December 19th, the comet makes its closest approach to Earth about 1.8 astronomical units away, roughly 270 million kilometers. That's close enough for the entire global astronomy community to coordinate what is essentially a full-spectrum diagnostic sweep. The International Asteroid Warning Network has pulled together a planet-wide campaign. The Hubble Space Telescope will capture high-resolution images and ultraviolet spectra. The James Webb Space Telescope will analyze infrared signatures and measure thermal characteristics. Ground-based observatories across the world will track the comet's motion, brightness, and chemical fingerprints. And amateur networks will provide nearly continuous monitoring, filling in the gaps no single telescope can cover. And the questions they're asking are exact, simple, and testable. Is there a debris cloud? If yes, then the missing mass mystery is solved. Large-scale natural outgassing would explain it. If no, the numbers stop making sense. What are the jet velocities? If they're the usual thermal speeds, 400 to 800 meters per second, then the comet is behaving normally. But if they climb into the thousands, we're dealing with physics outside standard sublimation. And if velocities reach tens of thousands of meters per second, then we may be looking at plasma, or something that behaves like propulsion. What chemicals are present? A normal suite of cometary molecules means a natural origin. Strong plasma emissions or unfamiliar spectral lines suggest something far more unusual. And most importantly, do the jets remain straight? If repeated observations from different angles all show the same rigid, non-spiraling structure, then the traditional rotation spiral model collapses. If the jets finally show curvature, then perhaps November's image was nothing more than a geometric coincidence. These measurements won't give us all the answers, but they will eliminate entire categories of possibilities. And if the data keeps leaning in the direction it has so far, if the jets stay locked, if no debris appears, if velocities don't match thermal predictions, then the idea that this object might be technological doesn't just stay on the table, it gains weight, not certainty, but enough plausibility that scientists will be forced to take it seriously. Now we're entering the part of the discussion that many scientists hesitate to say out loud, not because it is wild, but because it demands intellectual honesty. If 3I Atlas were not a natural comet, if it were built, if it were some kind of probe moving through our solar system with purpose, then what would we actually expect to see? Not what it is, but what it would look like if it were designed for an interstellar mission. Begin with the basics. Any long-duration spacecraft traveling between stars must deal with brutal environmental forces, thermal extremes, radiation storms, micrometeorites, thousands of years of drifting through deep space. The simplest solution, one we use on our own probes, is rotation. Spinning the body evenly distributes heat and wear across all surfaces. It provides passive stability without burning fuel. And the ideal spin rate is slow, steady enough to stabilize the craft, gentle enough to avoid tearing it apart. A rotation period of 16.16 hours fits perfectly. It is almost exactly what an engineered object would use for long-term durability. But rotation alone isn't enough for a probe meant to study a planetary system. Instruments must point in specific directions. Sensors, antennas, and cameras cannot simply spin aimlessly. Modern spacecraft solve this with attitude control systems, reaction wheels, tiny spinning masses that allow the craft to pivot without firing, thrusters. Some instruments remain perfectly still, locked on their targets, even as the rest of the body rotates beneath them. If 3I Atlas had such a system, the jets would behave exactly as they do now, straight, stable, holding a fixed orientation in space while the nucleus spins underneath. Next, consider its path into the solar system. An explorer coming from interstellar space would not approach randomly. It would align with the planetary plane, the thin disk where Earth, Mars, Jupiter, and all major worlds reside, because flying along that plane maximizes viewing opportunities. Instead of zipping above or below the solar system and glimpsing planets from afar, a probe aligned with the ecliptic could pass close to each world in sequence. 3I Atlas arrived with an inclination of only about 5 degrees from that plane. Natural objects can do that, yes, but for a reconnaissance mission, this alignment is exactly what you would choose. Then look at the trajectory itself. The path of 3I Atlas brought it near Mars in early October, near Venus shortly after, and it will pass close to Jupiter in March of 2026. For a random interstellar object, hitting multiple planetary flybys is extremely unlikely. For a craft designed to gather detailed data on major planets, these close approaches would be intentional. There is also the matter of timing. When did its most active and revealing behavior occur? Exactly when Earth could not observe it directly behind the Sun at perihelion. From our vantage point, the comet's closest solar approach was hidden from all ground-based telescopes. Only spacecraft with coronagraphs could see it. If something wanted to run operations, perform maneuvers, shed heat, or activate systems without Earth watching, this timing would be ideal. Coincidence? Possibly. Convenient? Absolutely. And then there is the gentle drift in its trajectory, the non-gravitational acceleration. Natural comets experience subtle pushes from gas jets, which act like miniature thrusters. But the magnitude observed in 3I Atlas is difficult to reconcile with the modest coma we now see. If a probe were making small course corrections, tiny thrusters pulsing occasionally would produce exactly this kind of motion. What makes all of this unsettling is not any single detail. It is that every element lines up naturally under one assumption, that the object is engineered. Rotation matches expectations for long-term stability. Straight jets match expectations for controlled orientation. The ecliptic alignment matches expectations for target system mapping. The planetary flybys match expectations for reconnaissance. The concealed perihelion matches expectations for unobserved operations. The acceleration matches expectations for course adjustments. None of this proves an artificial origin, but it does show that the idea is not absurd. In fact, it aligns cleanly with what we already see, far more cleanly than the strained natural explanations we have been forced to propose. It does not claim anything extraordinary. It simply asks a fair question. If a probe from another civilization were passing through the solar system, would it look much different from what we are observing right now? If 3I Atlas is using any form of active propulsion, even the faintest nudge to adjust its path or its orientation, then that propulsion must leave fingerprints in the simplest place imaginable, the jets themselves. Thrust always requires mass being pushed out the back. It doesn't matter whether you're burning chemicals or accelerating ions, something has to be expelled at high speed to create a reactive force. And at the speeds associated with propulsion, the behavior of those jets changes dramatically. Chemical propulsion produces exhaust moving at roughly 3,000 to 5,000 meters per second. Ion propulsion can reach 10,000, 50,000, even 100,000 meters per second. At those velocities, material could travel 3 million kilometers not in 3 months, but in hours, or at most a couple of days. And if the material crosses that distance quickly, the nucleus barely rotates during the journey. A handful of degrees, maybe a fraction of a turn, spiraling becomes invisible. The jets look perfectly straight. Even more interesting, the amount of material needed to generate measurable thrust is tiny compared to the natural mass loss of a comet. A few hundred kilograms of high-velocity exhaust every second can mimic the push created by millions of kilograms of slow, expanding gas. So if 3I Atlas were expelling a small amount of very fast exhaust, we would see exactly what we see now. Straight jets, no obvious spiral, subtle non-gravitational acceleration, and no massive debris cloud spreading into space. And if that exhaust is directed precisely, if the nozzle, so to speak, is kept pointed in the same direction, then it could also explain why the jets appear locked into place while the body rotates beneath them. This is not guesswork. December's spectroscopy will test this directly. Chemical propulsion leaves behind telltale signatures: water, carbon dioxide, nitrogen compounds, but in ratios no natural process produces. Ion propulsion leaves behind highly ionized atoms with sharp, unmistakable emission lines. If those lines appear, we will know we're looking at propulsion. If they don't, then this hypothesis collapses immediately. But suppose the jets are real engines. Suppose 3I Atlas is using propulsion intentionally. That leads to an uncomfortable but necessary question. Could a machine actually survive the journey? People raise a common objection. How could engineered systems last millions or billions of years drifting between stars? But material survival in deep space is not magic, it is physics. Cosmic rays damage electronics slowly. Shielding doesn't need to be perfect, it only needs to slow the decay enough for the mission to outlive its purpose. Power sources based on long-lived radioactive isotopes already exist. Plutonium-244, for instance, has a half-life of 80 million years. Other isotopes last even longer, and the deeper into space an object travels, the colder it gets. At temperatures just a few degrees above absolute zero, chemical reactions nearly stop. Metals don't rust. Lubricants don't evaporate. Mechanisms barely age. We have probes launched in 1977, Voyager 1 and Voyager 2, that are still functioning nearly 50 years later. Scale that robustness by a factor of 100 or 1,000, add better materials, better shielding, better engineering, and the lifespan of an interstellar mission stretches from decades to eons. If an intelligent civilization mastered interstellar travel, this level of engineering would be trivial, which brings us to the question no one can answer. If 3i Atlas is artificial, who built it? We have no idea. It might come from a civilization that flourished 1 billion years ago and vanished, leaving only silent machines wandering the galaxy. It might come from a civilization that still exists, receiving telemetry right now, images of our sun, infrared spectra of our planets, the unmistakable oxygen signature in Earth's atmosphere hinting at life. Or it might be one of countless probes launched by countless civilizations over galactic history, drifting through space on trajectories that occasionally intersect young, interesting planetary systems like ours. We may never know who built it, but we can determine whether it was built. Its behavior will tell us that much. There is also a statistical argument that scientists rarely discuss in public, but it matters here. The galaxy is more than 13 billion years old. It contains between 200 and 400 billion stars. Most of those stars have planets. If technological civilizations emerge even once in every million star systems, an extremely conservative estimate that still gives us 200,000 civilizations over cosmic time. If only 1% of them ever sent probes into interstellar space, that's 2,000 civilizations launching them. And if each of those civilizations deployed even a modest fleet, perhaps 100 probes in their entire history, that's 200,000 artificial objects roaming between the stars. The Vera Rubin Observatory will detect hundreds of interstellar objects in the next decade alone. Statistically, if artificial probes exist, we should expect 1 or 2 to pass through our neighborhood sooner or later. Maybe 3i Atlas is one of them. Or maybe it isn't. Maybe it is perfectly natural, perfectly explainable, simply unusual in ways we don't yet understand. Maybe all interstellar wanderers are carved by the same physics, and we're just learning how strange those physics can be. And that brings us back to a different version of the famous question known as the Fermi paradox. If intelligent life is common, where is everybody? One answer is simple. They are here, but not as empires, not as signals, not as civilizations broadcasting across the sky. They are here as probes, quiet, autonomous, patient, studying worlds the way we study exoplanets, silently gathering data. If 3i Atlas is one of those probes, we are not witnessing an arrival. We are witnessing a passing observer, continuing a mission that may have begun millions of years before humans even existed. Or we are simply watching a strange, beautiful comet behaving in ways we have never seen before. December will not give us absolute certainty. Science rarely does, but it will give us evidence. And that evidence may be strong enough to shift the balance between natural explanations and something far more extraordinary. 20 days remain until closest approach. Right now, 3i Atlas is drifting through Virgo. At 50 kilometers per second relative to the Sunday, every hour it glides another 180,000 kilometers through the darkness. Every day, more than 4 million kilometers. It's coming closer, not close in any dangerous sense, not close enough to trouble Earth, but close enough for something else, close enough for clarity. 270 million kilometers may sound enormous, but for our best instruments, it's an invitation. Telescopes are being booked, observation windows locked in, calibration routines are running in labs across the world. Astronomers are writing their command scripts, lines of code that will tell Hubble when to open its shutters, tell Webb which spectral channels to analyze, tell ground-based observatories when to switch filters, when to track faster, when to record. And the predictions are sharpening. There's no more hand-waving, no more vague speculation. Scientists are now saying aloud, in private meetings and internal memos, if it's natural, we should see this, this, and this. If it's artificial, we should see that instead. December 19th is the day those predictions begin collapsing into reality. One by one, they'll be confirmed or discarded. And beneath all this preparation, there's a tension that no one is willing to say in public, but everyone feels we may be standing at the edge of something that rewrites our understanding of the universe. Or we may discover that we've spent months chasing a mirage, a coincidence, a misunderstanding of perfectly natural physics. Either way, the waiting is almost over. What strikes me most about this entire situation is the quietness of it all. No alarms, no broadcasts, no planetary warnings. Just a faint smudge of light drifting through Virgo so faint that an ordinary person will never notice it. Most of humanity has no idea that anything unusual is happening at all. They get up in the morning, they go to work, they cook dinner, and all the while, an object from another star system continues its slow arc across our sky, carrying questions older than our species. Discovery rarely begins with fireworks. It begins with whispers. A few astronomers see something odd. They double-check, they compare notes. They send emails with phrases like, "This might be instrumental error," or "Can someone replicate this measurement?" They hop onto video calls late at night. They mass download data from shared servers. They argue. They hesitate. They measure again. They try to avoid sensationalism because science punishes overstatement harshly, and through that quiet, uncertain process, truth either clarifies or dissolves. There's a real possibility that 3I Atlas will pass through our solar system, fade into interstellar darkness, and leave behind only a stack of confusing observations, just enough to raise questions, not enough to answer them. That's the part nobody likes to admit. The universe is under no obligation to reveal its secrets cleanly. It gives us mysteries, not resolutions, yet we're about to try. In Maryland, inside the Operations Center for the Hubble Space Telescope, engineers and instrument scientists are finalizing the plan. Hubble will aim its ultraviolet spectrograph at the comet, an instrument capable of detecting molecules invisible at optical wavelengths. If 3I Atlas is shedding the billions of tons implied by its subtle acceleration, the ultraviolet light will betray it. Bright emission lines from hydroxyl radicals, carbon, sulfur compounds, signatures that scream massive outgassing. If those lines are faint, then the mass loss isn't real, which means the acceleration must come from something else. Hubble will also try to resolve the nucleus itself, searching for cracks, companion fragments, any structural clues that might explain the straight jets. 1.5 million kilometers farther outward, at the James Webb Space Telescope preparations mirror the same urgency. Webb's near-infrared spectrograph will measure carbon dioxide, carbon monoxide, methane, water vapor, dozens of molecules that map the comet's chemistry with extraordinary precision. Scientists will compare December's measurements with those taken in August, before perihelion. Did something change during its hidden passage behind the Sun? Did any new compounds appear? Did activity increase or decline in a way that fits natural behavior? Webb will also examine the nucleus's thermal emission directly, literally reading the heat across its surface. If any region is warmer than sunlight alone can explain, that's a clue. If the temperature distribution looks engineered, uniform, or strangely asymmetric, that's another. And in Chile, at the Very Large Telescope, teams are preparing ESPRESSO, the most precise Doppler instrument ever placed on a large telescope. Even though it was designed for exoplanets, ESPRESSO can measure the velocities of gas jets with breathtaking accuracy. If the jets are moving at 400 to 800 meters per second, the spectral shifts will be small but measurable. If they're moving at several thousand meters per second, the shifts will be unmistakable. And if the velocities reach tens of thousands of meters per second, well, then we're no longer talking about natural cometary outgassing. We're looking at something that behaves more like propulsion. Every instrument, every team, every observing run, all of it is converging toward one moment, when the data begins arriving. And when it does, the story of 3i Atlas will finally move beyond speculation and step into whatever truth the universe has been hiding from us. Professional observatories aren't the only eyes watching. Across the world, amateur astronomers are preparing their own instruments: 8-inch backyard telescopes, cooled CCD cameras, tracking mounts bought second-hand or assembled by hand. They're calibrating dark frames, checking star charts, updating ephemerides, and in living rooms, garages, and backyard observatories, they're joining a global network that never really sleeps. Organizations like the American Association of Variable Star Observers have already issued an alert. The British Astronomical Association's Comet Group is coordinating observers across the UK. Similar networks are forming in Europe, Asia, South America, Australia. When 3i Atlas sets for one hemisphere, it rises for another. Somewhere on Earth, someone will always have it in their sky. This matters more than most people realise. Comets don't behave politely. They don't wait for a scheduled telescope run. Outbursts can erupt in minutes. Jets can brighten suddenly or fade without warning. A subtle change in brightness might occur exactly at the moment when every major observatory on Earth is facing daylight. But amateurs fill the gaps. They form a continuous relay, passing the baton from time zone to time zone. With long exposures, they can capture jet structures professionals might overlook. With repeated brightness measurements, they can detect activity changes too brief for large telescopes to catch. And sometimes it's an amateur who notices something no professional saw: a faint asymmetry in a jet, a wobble in brightness, a strange colour. Someone experimenting with image processing in a way a research pipeline never would. Science advances not through isolated genius, but through hundreds of people adding their own small piece to a puzzle too large for any one person to solve. That's the spirit surrounding 3i Atlas right now. Collective vigilance, collaboration, and a quiet sense that something extraordinary might be unfolding. Meanwhile, scientists have begun drafting what some are calling the prediction matrix, a set of expectations that will tell us, within weeks, which hypothesis survives. If 3i Atlas is a natural comet, nothing more than an unusually carbon dioxide-rich visitor with exotic surface chemistry, then spectroscopy should reveal strong CO2 emissions, 10,000 to 100,000 kilograms per second of gas pouring off the surface. Ultraviolet data should show water and hydroxyl radicals. The coma should balloon outward to hundreds of thousands, maybe millions of kilometers. Jets might show faint curvature when viewed from exactly the right angle. Brightness should change according to well-understood thermal models. And velocities should remain moderate, 400 to 800 meters per second. If, instead, the jets are plasma, if electromagnetic forces rather than sunlight-driven sublimation are shaping the activity, then the data will look different. Spectroscopy should reveal highly ionized atoms, carbon ions, oxygen ions, molecular ions like Co+. Emission line ratios should indicate plasma temperatures above 10,000 Kelvin. Velocities could climb into the thousands of meters per second. The blue coloration recorded at perihelion might be explained by plasma emission. And the jets might appear straight not because they defy rotation, but because they escape so quickly that rotation has no time to bend them. And then there is the final possibility, the one everyone speaks of quietly, cautiously. If 3i Atlas is artificial, even minimally, the predictions tighten further. Spectroscopy might reveal unusual chemistry combustion byproducts if chemical propulsion is involved, or strange ionization patterns if it uses electric propulsion. Velocities could surpass 10,000 meters per second. Jets would remain perfectly straight no matter the viewing angle. There would be no massive debris cloud despite measurable acceleration. Thermal maps might show localized heating inconsistent with sunlight alone, and activity might fluctuate in ways that do not follow solar distance at all, patterns that look deliberate rather than thermal. The key is that each scenario, natural, plasma-driven, artificial, makes different predictions, testable predictions, predictions that cannot all be true at once. And that's what makes this moment so compelling. We aren't dealing with speculation drifting untethered in the dark. We have hard numbers, physical expectations, and instruments capable of telling these hypotheses apart. December will referee them. One after another, the possibilities will fall away until only one remains. And whatever survives that process will tell us, finally, what 3i Atlas really is. There's another strange element to all of this, one that feels almost as eerie as the observations themselves. Mainstream media isn't talking about it. A few science outlets have covered the basics. Space.com ran a cautious piece. Universe Today mentioned the unusual jet geometry. A handful of astronomy bloggers have been whispering about the November 9th image. But beyond that, silence. No evening news segment. No. Major headlines. No viral social media threads. Why? Part of it is simply that the story is difficult. Saying the jets don't spiral the way they should doesn't strike most editors as electrifying. It isn't a soundbite-friendly mystery. It requires diagrams, models, comparisons to other comets, an understanding of rotational kinematics. It doesn't fit cleanly into a tweet. Another reason is the scientists themselves. Nobody is claiming aliens. Nobody is making dramatic statements. Every interview features the same careful phrasing. We don't yet know what's happening. We need more data. And, without sensational quotes, major outlets don't see urgency. There's also a discomfort with ambiguity. Media prefers certainty heroes, villains, causes, consequences. They want the headline to say, "Scientists confirm X," not "Scientists puzzled, more study needed." And right now, this story is nothing but uncertainty. But all of this could change within weeks. If December's observations reveal jet velocities that don't match thermal models, if spectroscopy shows chemical signatures inconsistent with natural processes, if multiple independent teams publish analyses saying we cannot reconcile these observations with known comet physics, then the story will explode. And with that explosion will come chaos, public fascination, wild speculation, conspiracy theories, pressure for definitive answers long before anyone is ready. Scientists are already preparing for that possibility, drafting statements, discussing communication strategies, figuring out how to explain "we don't know yet" in a way the public will actually accept, because there's a historical precedent for what's happening right now. In 1967, a graduate student named Jocelyn Bell Burnell noticed a strange signal on the chart recorder of a radio telescope, a crisp, perfectly timed pulse repeating once every 1.337 seconds. The precision was uncanny, too regular, too sharp, too mechanical. For a brief moment, long enough to leave a note in the lab, they wondered whether it might be artificial. They jokingly labelled the signal Little Green Men 1. Then they found another pulsar, and another, each with a different pulse rate. The artificial hypothesis became unnecessary. Eventually the explanation emerged. Rapidly spinning neutron stars beaming radio waves like cosmic lighthouses. Not aliens, just a form of physics nobody had ever seen before. The key lesson is not that aliens are never the answer. It's that when something looks impossible, every explanation deserves a seat at the table until evidence rules it out. That's exactly where we stand now. The jets of 3i Atlas might turn out to be a natural phenomenon, something unusual, something rare, something that forces us to revise parts of comet science, but still fundamentally natural, or they might not. The only responsible, the position right now is to stay open-minded and wait for the data that's coming, and the clock is ticking. There's a way to think about the artificial hypothesis that doesn't rely on emotion or instinct, just numbers. Cold, impersonal statistics. The Milky Way contains roughly 300 billion stars. Modern exoplanet surveys show that planets are common, not rare, which means most of those stars have planetary systems of their own. Now, let's be extremely conservative. Imagine only 1% of those systems ever develop a technological civilization at any point in their history. That still gives you about 3 billion civilizations across the lifetime of the galaxy. Take it another step. Suppose only 0.1% of those civilizations ever attempt interstellar exploration. That's 3 million civilizations sending probes into the void. And then be even more conservative. Imagine each civilization sends out only 10 probes during its entire existence, barely anything at all. Suddenly you have 30 million artificial objects moving between the stars, spread across more than 13 billion years of cosmic history. Most of them won't survive. Collisions, radiation damage, gravitational encounters, interstellar space is enormous but not empty. But even if only 1% endure long enough to drift into other star systems, you're left with hundreds of thousands of ancient, functional probes roaming the galaxy right now. Spread those survivors through the thin disk of the Milky Way, and you get a density so low it sounds meaningless, on the order of a few dozen millionths of a probe per cubic light year. But this is where human perception fails us. Because with the Vera Rubin Observatory coming online, astronomers expect to detect hundreds of interstellar visitors every year. Over a decade, thousands. If even 0.1% of those objects are artificial, we should find several in the next 10 years. That means discovering an artificial probe isn't a 1 in a trillion miracle. Statistically, it's almost expected if civilizations are reasonably common and the galaxy has been sending objects drifting through the void for billions of years. So maybe 3I Atlas is just another natural wanderer from deep space. Or maybe it's something far older, far stranger, built by hands or frameworks we'll never see. And that leads to a question that feels unsettling the moment you speak it out loud. If an advanced civilization wanted to send probes through other star systems without alarming anyone, how would they design them? They wouldn't look like spacecraft. They'd look like debris, like ice-coated rocks that picked up dust over billions of years. They'd rotate gently for thermal stability. They'd align their instruments internally so nothing external needed to move. They'd take trajectories that seemed random but happened to pass close to interesting planets. They'd schedule delicate operations when hidden behind stars. They'd behave just within the boundaries of natural phenomena, just enough that a cautious, conservative species would hesitate to jump to conclusions. And they would rely on the one trait almost every scientific culture shares, the instinct to say, there must be a natural explanation. That's the part that keeps me awake at night. Because if you were designing a probe to avoid detection, you would count on the target civilization doing exactly what we're doing right now, looking at anomalies, shrugging, and saying, we probably just don't understand comets as well as we thought. Maybe that's exactly the right answer. Maybe we truly don't understand them yet. Maybe 3I Atlas is about to teach us something new and completely natural. But maybe there's a reason we find ourselves bending over backward to make the natural explanation work. If December's observations point toward artificiality, if multiple independent instruments all come back with results that can't be reconciled with conventional comet physics, the world won't change overnight. There won't be panic. There won't be spaceships emerging from behind the moon. There won't be contact. What will happen is quieter. A few papers will appear in scientific journals with careful wording. Observations inconsistent with known natural processes. Evidence suggesting directed propulsion. Behavior requiring non-standard modeling. Some researchers will accept the idea quickly. Others will resist, demanding more data. Debates will flare up in conferences and peer review threads. Hypotheses will be refined. Weeks will pass. Months. The arguments will trend toward one conclusion, not because anyone wants it to be true, but because the evidence continues pointing there. And slowly, a kind of global realization will start to settle in. Philosophers will debate what this means for our understanding of life. Religious leaders will consider how it fits into their doctrines. Governments will form committees, trying to decide what, if anything, must be done. People online will argue endlessly, but beneath all of that noise, one simple truth will take root. We would no longer be speculating. We would be knowing that someone else somewhere, sometime, built something that reached us. Knowing that intelligence is not unique to Earth. Knowing that we are part of a larger story unfolding across the galaxy. And even if we never contact the builders, even if they died 1 billion years ago, even if 3I Atlas is the only artifact we ever find, just knowing it exists would change us forever. 3 weeks remain. Right now, as you hear this, the object we call 3I Atlas is still drifting inward. Every second, it moves another 50 kilometers closer to its nearest approach. Every minute, 3,000 kilometers. Every hour, 180,000. A quiet, steady glide through the darkness. It does not know we are watching. If it is natural, it cannot know. If it is artificial and still awake, it might. Maybe it sensed Earth's radio noise long before we realized it was out there. Maybe it has been studying us while we were only just learning how to study it. But whatever its nature, it continues forward, following physics, or following programming, or simply staying on a path that was set long before humans ever climbed out of the dark, and we keep watching, measuring, fine-tuning our instruments, preparing for the moment when we will see it with the greatest possible clarity. December 19th, 2025. That is when everything sharpens. When the blur becomes a shape and the questions finally meet the data, mark that date, because whatever we learn, whether ordinary or extraordinary, will answer a question humanity has carried for a very long time. I want to be honest about something. We may not get clear answers this December. The observations could sit right in the middle, too strange to be comfortable, but not strange enough to be decisive. We might see jets that look perfectly straight at first glance, but show a hint of bending when viewed from certain angles. We might measure speeds that feel higher than normal, but not so high that they break the rules. We might detect chemistry that is unusual, but not unusual enough to close the case. And that is how science works more often than people think. The universe does not hand out clean solutions to clean questions. If this happens, if December leaves us in the grey zone, then the investigation will continue. More observations in the months that follow. More tracking as 3i Atlas moves farther away. Different telescopes joining the effort. New techniques applied to the same data. Squeezing out meaning we could not see at first. The mystery may not resolve quickly. It may linger. And that is frustrating, because we want a conclusion. We want to know. But reality is not on our clock. Sometimes we have to sit with the uncertainty, resisting the temptation to jump ahead. We let the evidence grow slow and steady until the shape of the truth emerges on its own. And that brings us to what is really at stake here. We are not deciding whether this is alien technology. That question is far too big, far too dramatic, and far too premature. The real question is simpler, and far more important. Does 3i Atlas behave like a natural comet, obeying every rule we understand? Or does it behave in ways that natural physics cannot explain? If nature can explain it even if it requires unusual chemistry or rare plasma effects, then we have discovered something new about how comets can behave. That is progress. That is science doing what it does best. But if nature cannot explain it, if every natural mechanism we test fails to match what we see, then we must be willing to take the next step, not shouting that it is artificial, but acknowledging calmly and honestly, this object does not behave like a natural comet. We need to investigate further. That is good science too. Following the evidence without fear, even when that evidence leads us into uncomfortable territory. There is something deeply human unfolding beneath all of this. Because how each person reacts to 3i Atlas depends on what they hope the universe is. Some people want it to be natural, a simple object, a frozen relic following the rules of physics and chemistry. That kind of universe feels stable, predictable, safe. Others quietly hope for the opposite. They have spent their entire lives wondering whether we are alone, watching the night sky with the belief, maybe the longing, that someone else might be out there too. If 3i Atlas is artificial, it means the universe is not silent. It means somebody else once asked the same questions we do. Both reactions make sense. Both come from deeply human places. But neither has anything to do with what 3i Atlas actually is. The universe is under no obligation to match our emotional preferences. It does not bend its behavior to comfort or excite us. Spectra do not care about our hopes. Jet shapes do not care about our fears. 3i Atlas simply is what it is. Our job is to figure out what that is, not what we want it to be. And that takes honesty, patience, and the willingness to accept an answer even if it lands far outside our comfort zone. And very soon, the instruments that can give us those answers will finally be pointed at it. The Hubble Space Telescope will take its turn first, beginning several days before the close approach. Its ultraviolet spectrograph will separate the faintest signals into clear, readable light. This is where we see the fingerprints of water breaking apart in sunlight, the glow of carbon atoms, the subtle shimmer of sulfur. If the gas production is strong, the signals will leap off the detector. If the gas production is weak, the absence will be just as obvious. Then the James Webb Space Telescope will follow, Its infrared spectrograph can see molecules that no Earth-based telescope can detect through our atmosphere. Webb will reveal how much carbon dioxide is present, how much carbon monoxide, how much water, how much methane. It will show whether December looks dramatically different from August, or if the production levels remain strangely steady. Webb can even read the temperature of the nucleus itself. If it is warmer than sunlight can explain, that matters. If it is colder, that matters too. Meanwhile, the Very Large Telescope will measure the speed of the jets with staggering precision. Even small changes in velocity create tiny shifts in the color of the light shifts that this instrument can detect with incredible accuracy. If the material is moving like normal comet gas, the numbers will sit low. If it is moving dramatically faster, the shift will be unmistakable. Across the world, dozens of ground-based observatories will capture long-exposure images night after night. And the amateur community, the same people who catch supernovae before the professionals do, will be filling in the gaps, providing constant coverage as 3i Atlas rises and sets across different time zones. All of that data will move fast. Quick reports will appear first, written in urgent scientific bulletins shared within hours. Early analyses will follow within weeks. And before half a year has passed, we will have a working picture, maybe incomplete, maybe surprising, but grounded in the best evidence humanity can gather. That is what is coming. And everything depends on what the instruments see. There are only a few ways this can go, and each one leads us toward a very different understanding of what 3i Atlas truly is. The first possibility is the simplest. Everything turns out to be natural. When the December data arrives, the telescopes might reveal strong gas, emissions, bright ultraviolet and infrared signals, and a giant, expanding cloud of material drifting away exactly the way a carbon dioxide-rich comet should behave. Maybe the jets really do curve, just a little, and the straight appearance in November was nothing more than the perfect alignment of viewpoint and timing. If that happens, then 3i Atlas becomes something else entirely, not a mystery, but a lesson. A reminder that interstellar comets can be stranger, colder, richer in carbon dioxide, and more unpredictable than anything in our own solar system. The anomalies would still be real, but they would join the long list of rare but natural behaviors that nature occasionally displays when we look closely enough. Most scientists quietly expect this outcome. It is the safe one, the comfortable one, the one that lets the universe remain familiar. But there is a second possibility, the one nobody likes to talk about. The data might land somewhere in the middle, muddy, confusing, halfway between normal and impossible, gas production that is neither high nor low, velocities that are faster than they should be, but not so fast that we can rule out natural explanations, jets that look perfectly straight in some images and maybe, possibly, show the tiniest hint of curvature in others. If that is what we see, then the mystery does not end, it deepens. Scientists will publish papers that disagree with each other. Arguments will spark in conference halls and video meetings. New observing campaigns will launch in January, then February, then March. And the question of whether 3i Atlas is natural or not will remain suspended in uncertainty, maybe for years. This outcome frustrates everyone. It leaves the door open, but only a crack. It keeps both possibilities alive without letting either one win. And then there is the final possibility, the one that changes everything. The telescopes might see almost no gas at all, nowhere near enough to explain the strange acceleration. They might detect velocities far beyond what sunlight can produce, thousands or even tens of thousands of meters per second. They might reveal jets that remain perfectly straight from every angle, never curving, never spiraling, never behaving the way a rotating comet should behave. They might show chemistry that does not match any natural process we know. They might detect heat where there should be cold. If that happens, then the natural explanation breaks. Not because scientists prefer the alternative, but because the data forces their hand, because every tweak to the models fails, because every natural mechanism collapses under the weight of the observations. In that scenario, the idea that 3i Atlas could be engineered, built, designed, guided moves from the speculative edge of scientific conversation into the center of it, still not proven, but no longer dismissible. Papers would begin to appear with cautious, deliberate language, non-standard physical processes, behavior inconsistent with natural cometary activity, origin uncertain, further investigation warranted, and engineers would quietly start running the numbers. How fast can we build an intercept mission? How soon can we launch? How close can we get before 3i Atlas slips back into interstellar darkness? Because a discovery like that, a real physical object showing evidence of engineering, is not just an astronomical event, it is a turning point in human history. And within a few weeks, we will begin to see which path the universe has chosen. The moment is almost here. On the 19th of December, 2025, the object we call 3i Atlas will be as close to Earth as it will ever get on this pass. Not close in any dangerous sense, still nearly twice the distance from Earth to the Sun, but close enough for our instruments to finally see it with the clarity we have been waiting for. At that distance, moving 50 kilometers every second, it will stay within prime observational range for just over 2 weeks. From the 12th of December through the 5th of January, humanity will turn its telescopes, its sensors, and its collective attention toward this single traveler from deep space. Hundreds of observatories, dozens of spacecraft, thousands of scientists, students, and amateurs giving their time and their energy to watch one faint object drifting through the night. All of them aiming at the same single question: what exactly are we looking at? In 6 months, we will know far more than we know now. Maybe we will have an answer. Maybe we will only have clues that complicate everything further. But either way, we will learn. And learning, especially when it challenges us, is the whole reason we look up at the sky in the first place. If you step outside tonight, after midnight, and look toward the east, you will see the constellation Virgo rising above the horizon. Somewhere in that, a quiet patch of sky, far too faint for your eyes to detect, 3i Atlas is gliding forward through the darkness. You will not see it, not even with binoculars, but it is there, right this moment, crossing millions of kilometers of emptiness, reflecting sunlight that left the sun 8 minutes ago, moving along a path shaped by gravity, momentum, and maybe something more. It has been traveling for longer than our species has existed. Its age is beyond imagining. Its nature is still unknown. Its purpose, if it has one, remains a mystery. But it is in our sky. We are watching. We are measuring. We are asking questions that have no easy answers. And in just a few weeks, our clearest view yet will arrive. The universe does not hand over its secrets quickly. It reveals them reluctantly, in fragments, in hints, in puzzles that take patience to assemble. But we are learning, slowly, persistently, curiously. We are learning to read what the cosmos is trying to tell us. The answer is almost here. December 19th, 2025. Only 17 days away. That date marks the moment when the object we call 3i Atlas reaches its closest approach, its moment of greatest clarity, when our telescopes, spectrographs, and sensors finally collect data detailed enough to confirm what this visitor truly is, or at least rule out what it cannot be. Until then, all we can do is wait. Not quietly, not passively, but in the way scientists always wait, by preparing, calibrating, coordinating, and thinking. The universe follows its own timing, not ours. We can only meet it at the moment it reveals itself. And that moment is coming. What we already know is not speculation. It is established fact. 3i Atlas is real, a solid object several kilometers wide. It comes from interstellar space. It rotates once every 16.16 hours. It produces jets that stretch for millions of kilometers, jets that remain unnaturally straight even though the object spins. Beneath them, it has accelerated in ways that gravitational forces alone cannot explain. And it carries 11 other anomalies, each rare but possible on its own, yet strangely improbable when gathered together in one single visitor. Those facts are not guesses. They are measured, observed, confirmed by multiple independent teams. The only thing we do not know is what those facts mean. That is the uncertainty we are living with. And strangely, there is value in that uncertainty. It forces humility. It reminds us that even after centuries of exploration, the universe still surprises us. It reminds us that our models are not perfect, our assumptions are not absolute, and our understanding is always limited by the questions we have not yet asked. Uncertainty keeps us curious, keeps us honest, keeps us searching for answers instead of settling for comfortable guesses. And now, we stand at the edge of the biggest question of them all. Right now, in these final days of November 2025, an object from another star moves silently across our sky, showing us behavior that refuses to fit neatly inside the physics we know. Jets that should twist are perfectly straight. Acceleration appears without debris. 12 anomalies align into a pattern that feels less like coincidence and more like a message we have not yet deciphered. And in 17 days, the sky will give us the data we need to test every theory we have built around this visitor. Maybe the explanation will be natural, something exotic, but still rooted in physics we understand. Maybe it will involve plasma behavior we have never observed in a comet before. Maybe it will involve materials or chemistry that reshape our models of cometary activity. Or maybe, just maybe, it will require us to consider that not all objects wandering between the stars are simply frozen rubble left over from planetary formation. Maybe this one was made, or guided, or designed. Not proven, not assumed, just possible. And that possibility alone is enough to demand serious investigation. If you have followed this entire journey through the physics and the contradictions, through the numbers and the oddities, then you understand why this matters. You understand that real mysteries are rare and precious. You understand that unanswered questions push science forward more than comfortable explanations ever could. You understand that uncertainty is not something to fear, it is something to explore. 3i Atlas, whatever it is a reminder that the universe is wider, stranger, and more intricate than we expect. It reminds us that the dark spaces between stars are not empty. They are filled with travelers, with fragments of ancient systems, with objects carrying chemical histories written long before our world existed. Some of those travelers are ordinary, some are extraordinary, and every so often, one appears that forces us to rethink everything we thought we understood, so we prepare. Telescopes are aligned toward Virgo. Spectrographs are calibrated with precision down to fractions of a wavelength. Data teams across continents synchronize schedules. Amateur astronomers ready their backyard observatories, filling the gaps between major facilities and providing the constant monitoring only a global community can achieve. All of us professionals, hobbyists, the curious, the skeptical, are watching a faint point of light drifting through the inner solar system, waiting for December 19th, waiting for that window when the universe opens just wide enough for us to see a little more clearly, waiting to discover whether the jets remain straight, whether the gas production fits any natural model, whether the mystery resolves or intensifies. Whatever the answer turns out to be, we will learn something. Something about comets, something about interstellar objects, something about the kinds of phenomena the cosmos is capable of creating, and possibly something about whether intelligence has ever reached out across the vast distances between stars. One thing is certain. 3i Atlas came from somewhere else. It travelled through darkness older than the human species itself. It drifted through regions of space where no sunlight shines, across distances so vast that even our fastest spacecraft would take tens of thousands of years to cross them. And yet here it is, in our sky, in our time, passing close enough for our brand new instruments tools that did not exist a generation ago to study it in detail. Maybe we are seeing a natural object doing something unexpected. Maybe we are seeing the results of physics we do not yet fully understand. Or maybe we are witnessing something built long ago by someone we have never met for reasons we can only guess. Whatever it is asking us one simple question. Are you ready to follow the evidence wherever it leads, even if the answer is nothing like what you expected? December will bring the data. January will bring the first analyses, and by the spring of next year, we will finally know whether this is simply a strange comet from another star or something that changes everything. The 12th anomaly sits in front of us. The jets that should twist remain straight. The pattern that should not exist keeps revealing itself. And the universe, vast, silent, ancient waits to see whether we are ready for the truth, whatever that truth may be. Clear skies, everyone.